Hey everybody, welcome back to the Byte Attic. Today is again a very special episode for me. Well, you're probably getting used to my saying that every episode is special, but this one is really special because this is a ZX-81 board, a ZE. It's a computer released by Sinclair in 1980. And this was the first computer of my life, not this specific unit, but AZX81 was the first computer I ever touched when I was, I don't know, 6, maybe early 7 years old. I've learned to program BASIC on these little things. It was the beginning of what has become a 24-year-long career in high technology, including computer engineering. So yeah, it doesn't get much more special than that. I've acquired this board. It does not have a very important chip, the ULA, but I do have some ULAs here. I don't know whether they work. These three are ZX81 ULAs. Some very early. This is from week 30 of 81, this is week 32 of 81, and this is week 45 of 82, almost 83. So this is the most recent one. They have been pulled from boards, so and I don't know whether they work because the boards were not complete, but at least we can have a go, putting one here to see if it works. I also have a bunch of processors here. Z80, which is this processor here, but this may be working. I may want to replace it anyway and put a modern CMOS equivalent. And this is a 32 kilobyte modern CMOS SRAM, or static RAM. It basically means that unlike a dynamic RAM or a DRAM, these SRAMs do not need the refresh signal from the Z80, which sort of reminds the memory of what its own contents are. Otherwise, the DRAM would forget its contents because of leakage, basically, electric leakage. I plan to replace these two memory chips here, which together form 1 kilobyte. It's not enough memory for you to do anything. I plan to replace with this chip, out of which 16 kilobytes are addressable by the Z80 on this board. So instead of connecting expansion here on the edge connector at the back, I would just put 16 kilobytes of addressable memory on board. That's the plan, and then do a few other improvements, because this is pimp my 8, so there has to be some pimping. I think I will replace these jacks here, these 3.5mm jacks, with gold-plated ones, because I need to use sound to load the program and record a program on this architecture. I don't want to use a connector here with a SD drive. So I need this jacks to be perfect. I will probably also change this linear voltage regulator here for a modern thing, which I can show you right now. This is a buck converter, or a DC to DC power supply. It does the same thing this guy does. It converts the 9 volts that come in here through this jack into 5 volts regulated. But this guy here, what it does, it takes 9 volts, puts out 5 volts regulated, and the remaining 4 volts it dissipates as heat. And the ZE has a very small, thin, narrow case. I don't want heat to build up inside, because then the lifetime of the chips will be reduced. They will live shorter. And this guy here, what it does, it goes from 9 to 5 regulated, but instead of doing this by dissipating the extra 4 volts, it just switches itself on and off thousands of times a second, so the voltage remains at 5. So it switches itself on, then the voltage climbs quickly to about 5, then it overshoots 5, and then it switches itself off. The voltage comes down a little bit below 5, and then it switches itself on again. The voltage goes up a little bit over 5. So you will get 5 volts with a little ripple, but this ripple is filtered out by a capacitor inside this thing, one or more capacitors. So you get 5 volts clean, regulated here, or on this pin, without dissipating a lot of heat. So I would do this. And this is the gold-plated jack that I alluded to. I want to replace this one with this. I have to cut one of the pins because this one only has 3 pins, but it's no problem. So let me walk you through the board as it will be, not as it is right now. But maybe before I do that, a quick intro to the ZX-81 architecture. And it is a very simple architecture. Let's start from these 3 chips here. These are memory chips, RAMs. The board allows for 2 options on the Sinclair ZX-81. Either you have 2 small RAM chips, IC4B and IC4A. This is what my board has. Or you have a larger RAM chip. And this is what I'm going to do. I'm going to get rid of the 2 small ones, and I'm going to put a larger one here. In fact, one larger than Sinclair predicted or would accommodate on the board. So by putting this larger chip here with 16 kilobytes of addressable RAM on board, we have to carry out some relatively extensive modifications, but we are going to see that later on in this episode. Of course, the system also has a ROM, a read-only memory with the instructions that the computer needs to execute immediately upon starting up. And the 2 main computational resources are the CPU, the central processing unit, which performs the calculations entailed by the application, and a ULA, an uncommitted logic array, which is the sort of the conductor of the orchestra. It's the chip that brings the system together, coordinates the activities across the different components of the system, and makes the computer works as an integrated whole. So this is the conductor, the ULA. There are of course, input and output devices. The main input device is a keyboard, which hangs here from the address bus. I'm not going to talk much about that. And then there is a radio frequency modulator, which prepares a signal that can be displayed on the television, and that's the key output device of this architecture. There are 2 main buses. One here in yellow is the address bus, which the CPU, for instance, can use to broadcast an address to the RAM and or to the ROM in order to fetch an instruction or fetch some data it needs. And then there is, of course, the data bus, where the data that has just been addressed is actually communicated, for instance, back to the CPU. There is also here on top a sort of control bus. These are control signals like interrupt request, memory request, chip select, read and write signals. So these are control signals that allow for the system components to be synchronized, so they don't step on each other's toes, so to say. But I'm not going to talk much more about it. It's a fairly simple control bus. There is also this bank of pull-up resistors here, 10 kilo ohm resistors hanging from the 5-volt power rail. And what they do is they prevent undefined values from floating here in the data bus. If no chip is putting a value on the data bus, then the data bus sort of floats. It has an undefined value, an undefined voltage level, somewhere around 2, 3 volts, whatever. And if one of the system components, say the CPU, were to read in that undefined value, thinking that it's a proper value, that could lead to error. So whenever nobody is forcing a value on one of the lines of the data bus, these pull-up resistors will pull that line up and enforce a logic 1 value in there. So no data bus line will ever float. They will either be defined by system component, or the pull-up resistors will pull that value up just under 5 volts. So it will be a logic 1. Now, very important and very idiosyncratic, very particular to the Sinclair architectures are these bus splitters here. There are 2. One in the data bus, one in the address bus. I'll talk only about the one in the data bus. What this thing does, it's a bank of 8 resistors of 470 ohm. They split the bus into 2 parts, a lower part in here and an upper part between the ULA and the CPU. And the idea is the following. Suppose the CPU is fetching an instruction from RAM, then the RAM will put the instruction on the data bus and the CPU will read it in, and on the basis of that instruction it will know what to do next. It will execute that instruction in the next opportunity it has.
But the ULA, remember, is the global system coordinator. It is the master of the orchestra, and it may not want the CPU to execute the next instruction. It may want the CPU to wait, to stop for a moment. So what this bank of resistors here, this bus splitter, does, it allows the ULA to overwrite whatever is on the data bus as far as the CPU is concerned. So if there is whatever value is in here on the lower part of the data bus, the ULA can overwrite that value on the upper part, and that's what the CPU will see, whatever value has been overwritten on the data bus by the ULA. For instance, a no-op value, a non-operation, which causes the CPU to just sit and wait. Now, this is in essence an analog solution to what is essentially a digital arbitration problem. It's a problem of bus arbitration. Who has access to the bus? Who is authorized to put a value on the bus? Today, and even back then, but especially today, we solve this through combinatorial logic, through digital logic, using bus arbiters, bus controllers, bus interfaces, and so on. But Sinclair, in order to make this architecture as cheap as humanly possible, got rid of all that combinatorial logic, which is expensive, and just put an extraordinarily cheap array of 8 resistors, which essentially costs nothing. And it works, and the reason it works is that, whatever the voltage level, even if it's not a perfect 5 volt, if the voltage level is above a certain threshold, it will be interpreted by the CPU as a 1. Even if it, 3.8 volts, it's above the threshold, it will be a 1. Similarly, if it's below the threshold, even if it's not perfect 0 volts, it will be interpreted as a 0. So the voltage levels here will be all over the place, but because of this thresholding, the CPU can still understand what the ULA was trying to tell it, was trying to make it do. And it works. But if you were to put an oscilloscope on these lines, which we may do later in this episode, you would see that you don't have nice, clean square waves here, whose value is either 0 or 5 volts and oscillate between the two very quickly. You would have semi-sinusoid waves in here, shark fins, and all kinds of crazy logic, crazy voltage values oscillating between 0 and 5. And it works because of the thresholding. And the reason it will be all over the place is that, look, the ULA will be putting voltage levels here that conflict with the voltage levels here on the lower part. And they are electromagnetically connected. Despite this resistor splitter in here, the voltages still interfere with one another. So you have interference between the values that should be in here and the values that are effectively in there. And there will be this crosstalk, and the result will be voltage levels anywhere in between 0 and 5 volts. It is a miracle that this works at all. It is such a cheap hack, but it speaks to the ingenuity of the Sinclair engineers pressed to come up with an extremely cheap, beyond reason, a cheap computer, and they still managed to come up with a working solution for that. It may not be very robust. If there is some other problem in the system, some other source of noise, the data here on the data bus probably will be corrupted much more quickly than it would be if you had done it correctly or in the traditional way, in the by the book way. But hey, these computers are still working today after 40 years. So who am I to say that this was crap? I mean, this was an incredibly ingenious solution to make this computer cheap. So this is the ZX-81 in a nutshell.
Welcome back. So the way it will look like is, well, I'll put a socket first, but the ULA will be here. And so the way it works is the following. 9 volts unregulated, well, in my case regulated because I will be using a modern, let me show you. I'm using a modern switch mode power supply instead of the original ZX-81 power supply, which is terrible. This one allows itself to be, you can set what the output voltage is that you want, in this case 9 volts, as you can see here. And so it will get mains voltage here, in my case 230 volts, and it will put out 9 volts through this 3.5mm jack. This power supply is very general purpose. It accepts different jacks. I'm just using 3.5 millimeters because that's the one the ZX-81 requires. But there are many options of jacks that you can put in here. I would try to link information about this power supply in the description below. So this is what I will be using. So in fact, we will be getting 9 volts already regulated here, which in this case here, this linear regulator brings down to 5. I will be using a buck converter in its stead. And then there are 5 main chips on this board as it is right now. This is the Z80 CPU. It performs all the calculations involved or entailed by an application. This is the ROM with the instructions that the computer follows upon being turned on. It also has the basic interpreter in here. These are 2 memory chips. You can look upon them as one memory of a 1 kilobyte. And this is the ULA, or the uncommitted logic array, like in the ZX Spectrum of the previous episodes. And this is what binds the entire computer together. This is what brings everything here together in the form of one unit, one computer. Like in the ZX Spectrum, there is content memory. This RAM here is used both for user RAM, but also for video RAM. So both are mapped in here, video and user content. So 1 kilobyte is already very, very little, but most of that is still reserved for video, which the ULA needs priority access to. So you're left with bytes to do anything useful with this computer. And that's not really likely. That's why I'm going to upgrade this to 16 addressable kilobytes. Then we can do some more. And then around here, there are 2 kinds of things going on. Part of this circuitry here is the clock. Like in the ZX Spectrum, the ULA produces the clock signal for the CPU, and it's the ULA that produces this signal here, which is the composite video signal, black and white in the case of this architecture. So part of it is related to taking the clock signal from the ULA, boosting it or buffering it, improving the signal, and passing it on to the CPU. And another part of it has to do with the control logic of the processor, signals like memory select, reads and writes. It's a kind of control bus of the architecture. And I don't know which one is the clock, which one is the control logic. I would have to look it up, but it doesn't matter. These are the keyboard connectors, ribbon connectors, and this is the RF modulator. This is the carrier oscillator, and then the composite signal going in here is used to modulate the carrier signal with the video information, which then goes out through the RCA jack.
And of course, we mustn't forget the 2 resistor banks that split the data bus and the address bus as well.
That's pretty much it. So the first job today, let me put this back because these are very delicate chips. First job today is to install a socket on the board. This board obviously has had the ULA pulled out at some point. And I want to put a socket in there so I can plug one of my ULAs back and see if the thing works at all. That's the first step. Now, you need some discussion here too. Normally, I use these sockets. These are precision sockets. Each of the contacts here sort of hugs the chip's pins from every direction. They are very good. But today, despite these being very good, and normally I use them instead of anything else, but today will be an exception. Here, let me put this back. Today, instead of this, I will be using this. This is a cheaper socket. It's a lower quality. I normally don't use them, but there's a very good reason I will use it today. I want to keep the option open of at some point putting a modern ULA replacement here instead of one of the original Sinclair ULAs. And these modern replacements are built on a PCB about this size, a little daughter board, and the pins are thicker than a normal chip's pins. The pins of the modern ULA replacement will not fit in these tiny little holes here. Only real chips will. The modern replacement will have thicker pins that will fit into these contacts, which are much larger and hug the pins from two sides. So not as good as this one, but it keeps the option open for using a modern ULA replacement. So I'm going to install this one, and that's what I'm going to do right now. And now I'm going to inspect for possible short circuits between two neighboring pins. They are not shorted, I already inspected visually, but this is good practice. It's good to do it in a systematic way. I'll do it from the contacts of the socket itself. If they contact like this, there will be a beep. So we don't want to hear any beeps. That beep was just that I accidentally touched one with the other. And it's good to do that because although you can inspect the pads below where they are exposed, the solder flows through the via to the top side. That was just an accident. To the top side of the board underneath the socket, and it can create a blob underneath the socket on the top side that you are not able to see visually. You are not able to inspect visually. So that was an accident. So it's good practice to check for continuity with the multimeter across neighboring pins, just in case you accidentally created that blob of solder right under the socket on the top side of the PCB. If you did that, it's no problem. You can use the desoldering station and undo it and do it again properly. But if you only find it out after you have put the chip in there and turn on the computer, you can fry a chip or you can damage a chip. So I'd rather do it now, even though I'm pretty sure that I didn't make that mistake. Now, to make it a little easier to put the chip in, although this contact is completely clean, it's new, I will put a little bit of the second step of the contact cleaner to cover it with a little protective lubricating film. What we are going to do now is clean the chip itself. Yeah, I'm going to use the ULA from the end of 1982 in the hope that this one is good. So the first thing I will do is clean the terminals with this mildly abrasive fiber pen, just to make sure that they will contact well. Because this socket hugs the pins from both the inner and the outer part, both sides. I'll clean this on both sides as well. Okay, now blow away some of the fiber. With compressed gas. And now I put contact cleaner on the chip's pins as well. And now we do it in 2 steps. There we are. That's our ULA. Ready for testing. Okay, here is our ZE with the ULA put on its socket, its newly installed socket. It doesn't have a on-off switch, so I'll be using this. The TV is in there. It should be in the right channel. So let's see. 3, 2, 1. Yeah, there is a prompt. I see the cursor there. Some funny interference. I'm using the RF modulator, this thing here. I think the next thing to do is to do a composite modification so we get a clearer image. Before we continue and start changing things, I just wanted to show you how the composite signal looks like. It's easy to interpret this signal on the ZX-81 because it only produces black and white. So the composite signal only has 3 states: black, white, and the synchronization pulse. And it comes straight from pin 16, if I remember, of the ULA. It's not even buffered in between. The pin is wired straight into this wire here that goes to modulate the carrier signal in the RF. Lower it a little bit so you see. So these are the 3 states that you see in the composite signal. Here on top, it's the highest voltage. That's the white. That's the white in the background that you see on the screen. Here in between, one level lower here in between, here and here, that's supposed to be the black. The cursor is black. So what you see here is, as the signal scans a line, only a little bit is black, and that's the cursor. And the lowest level that you see here, that's the synchronization pulse. Yeah, just wanted to let you see that. And